Hi everyone, today I want to talk a bit about asymptotic analysis, which is a tool we use to measure the efficiency of our algorithm. So as a core, asymptotic analysis asks, as the input size grows very large, how does the running time of our algorithm grow? Instead of focusing on the exact number of seconds of a program takes, we focus on its growth rate. This helps us compare algorithms in a way that is independent of computer hardware or programming language. And now within this analysis, we usually talk about three different types of bounds. The first one is upper bound, or big O. Think of it as the worst case scenario. For example, imagine a runner at an on track. The upper bound is like the longest time the runner could possibly take to finish the race. And there's also the lower bound, or big omega. This is the best case scenario. It's like if the runner found the perfect shortcut and finished the race in record time. And the third one is tidebound or big data. This is where the two come together. It represents the true growth rate of the algorithm, like the runner's typical performance when we consider both limits. And one thing to note here, the tidebound isn't always a fixed number. Sometimes the gap between the best and worst cases is wide. And in that case, big data may not exist. But when it does, it gives us the most practiced picture of how an algorithm scales. And why does all of these things matter? Because in computer science, efficiency can be as important as correctness. Let's say we have two sorting algorithms, bubble sort with O n squared and merge sort with O n log n. For small inputs, they may both finish quickly. But as the input size grows to millions of elements, the difference becomes huge. This is where asymptotic analysis gives us insight. It tells us which algorithm will still be practical as problems scale up. This connects to the larger picture of our computer science journey. Whether we become software engineer, data analyst, data scientist, efficiency is always a concern. And industry programs often runs on massive datasets or serve millions of users. So writing code that works is just step one. Writing code that scales efficiently is what makes system reliable and cost effective. And now let's kind of reflect on a specific example. If we compare O n log n and O n squared in the limit as n gets very large, O n log n is always faster because n squared grows much faster than n log n. But if the input size is small, the story changes. O n squared algorithms are often easier to implement, and their hidden constant might actually make them faster in practice for small datasets. So here's my question. Do you think if it could ever make sense to choose an O n squared algorithm over an O n log n one if we know the input size will always stay small?